I went ahead and photocopied homework 3 and homework 4. We'll probably finish up most of homework 3's material today. Start on homework 4's material. Homeworks 1, 2, 3, and 4 are the material covered on your first exam, which is when? 2 weeks from today. And homework 3 will be due, that's homework 3, correct? Yes. Next Wednesday. Homework 4 will be due the day of the exam. And I'm not sure, but I plan on actually having from 12:30 all the way to 2 p.m., that's an hour and a half, that's 10 extra minutes, available for you to complete the exam. So please plan accordingly. Any questions about that or about anything with Chem 400? Due dates? We're really rolling now because there are no breaks, there are no holidays. All right, well, make sure you pick these up. These are available on the Chem 400 website already. Speaking of the Chem 400 website, it has so much information on it. And added just yesterday was a link to the videos of the lectures. So if you want to go rewatch anything, add a laugh track for all my very bad jokes, that's fine. Anyway, so they're available to you. Now, where were we? We were talking about electrolytes. And we said that last time too. We said there are 3 types of electrolytes. We've now at least started to talk about all 3 of them. There are strong electrolytes, there are weak electrolytes, and there are non-electrolytes. And to be any of those 3 things, you must dissolve. So, and then we said there was a 4th category called insoluble. But now we have, and we said that strong electrolytes, when they dissolve, and we talked about what a dissolving reaction is. A dissolving reaction has something on the reactant side. Could be solid, liquid, or gas, that's true. But on the product side, everything is aqueous. And the question is, what state are those aqueous things in? For strong electrolytes, everything on the product side was ions, everything, 100%. For non-electrolytes, 0% were ions, and they were all whole molecules. And for weak electrolytes, well, weak electrolytes are the strange one, because we said that, yes, acetic acid and all weak electrolytes dissolve, but they make a small percentage of ions. Okay? And there's 100% stuff on the product side. I think that was a question. I forget who had it. But when the other 5% of this breaks up, it breaks up into 2 parts. So this is the total of the other 5% or less than 5% here. And this is deals with the fact that on homework 2, moles and molecules are not conserved. We can have more parts on the product side than we start with, because molecules break down, or in this case, dissolve and form ions. Any questions about that? I have one more thing to say about weak electrolytes right now, and I'll have plenty to say. Because whole molecules make up greater than 95% of the species in solution, whole molecules are considered the dominant species. And this will be important when we write total ionic and net ionic equations coming up. But I'm going to write here, dominant species are whole molecules. No, dominant species is whole. I don't know, I got lost in the English there. Dominant species, I think that's singular, is whole molecule. Oh, there we go. If you're not sure, add quotes and it makes it a thing. Well, anyway, hopefully you get the idea. And this will come up again though. Dominant just means present in the largest percentage. Now, solubility rules to memorize. We talked about this last time. Start at the top and work your way down. All common compounds of group 1 and ammonium ions are soluble. All nitrates, acetates, perchlorates, and chlorates are soluble. Know rules 1 and 2 very well. and that will help you. As you go down, we said all binary compounds of the halogens, other than fluoride, with metals are soluble. My favorite exception to the solubility thing here is silver chloride. Silver chloride is insoluble, and that's what part of what Rule 3 says. And really what Rule 3 says is that almost every other chloride, bromide, and iodide is soluble, but there are some exceptions. Questions about that? If not, then the take-home message here is illustrated in this picture. For if you have a non-electrolyte, it dissolves into solution for a homogeneous mixture. Run electricity, or attempt to run electricity through the solution. There are no ions, no current flows, no light bulb lights on. Strong electrolyte, strongly lit light bulb. Weak electrolyte, low percentage of ions, enough to weakly light a light bulb. Okay. Good. Our third reaction type, double replacement reactions. And within that, there are 3 types. Remember when it says reaction type, that means I can ask you to write that reaction. And we will do several examples of this. What happens when a container of potassium iodide is added to an Erlenmeyer flask of lead to nitrate? I guess that should be a subscript. Well, you start off with 2 solutions that have ions in aqueous ions. Then when they mix, they form a solid. That solid is a yellow color. Solids, when they form as a result of double replacement reactions, are called precipitates. And they are solids, so Another place you run into the word precipitate is when they talk about either snow, rain, sleet. Those are called types of precipitation as they fall from the sky. It's not the sky, but they are falling generally towards the bottom of the beaker, or in this case, Erlenmeyer flask. The precipitate is the solid. And our question when we do these kinds of reactions is, when we know our solubility rules, can we predict what the solid will be, or even if a solid will form? And you'll see this, and this is actually one of the problems very similar to this on homework 4 now, so we are talking about homework 4. Write the overall reaction, total ionic equation, abbreviated TIE, and the net ionic equation for the reaction that occurs when a test tube of potassium iodide is mixed with a test tube of lead 2 nitrate. So exactly what I just showed illustrated here. The overall reaction, and just a quick check-in, how many people did this in Chem 300? I think a lot of you did, if not all of you. In fact, if you're looking at lab number 3, which is I know a couple weeks away, I think you did it in Chem 300 almost exactly. That's how important lab 3 is. We're going to make you do it again in Chem 400. So overall reaction shows stoichiometry. And of course, stoichiometry is the fancy word we use so that when you balance it, you can do gram to mole to mole types of calculations. The overall reaction here, potassium iodide, which, according to rule number 1, all group 1 ionic compounds, potassium is in group 1, will be soluble. That's how we know to write aqueous after that. And I should point out, as I write all these compounds down, this reaction always has phases, solid, liquid, gas, aqueous, and you are expected to write them. Okay. So it's potassium iodide, it is aqueous, plus lead 2 nitrate, Rule number 2 says all nitrates are soluble, so that's going to get aqueous. Double replacement reactions, take the positive cation, which is K+, on one compound, pair them with the negative anion on the other one. So one of my products is potassium nitrate. And that is aqueous because all potassium, all group 1s are soluble, all nitrates are soluble. I wish there was a thing called soluble squared, but there is not. But that is just plain soluble. Take the lead 2+ here, pair it with the I- here. You'll need 2 of the iodides, and that's also shown over there. And if you look at your solubility rules, you will see that lead 2 iodide is an exception to the fact that most iodides are soluble, and it is insoluble. So insoluble things show up as solids. Is this balanced? Nope. It is not. You look at 2 iodides and only 1 over here, 2 nitrates and only 1 over there. So I've just balanced it. These are pretty straightforward to balance in my mind because instead of doing elements, think about entire ions. I have 2 nitrates, so I better have 2 nitrates on the other side. That's how I balance double replacement reactions. Anyway, lots of ways to balance. Shows stoichiometry just means that now I know 2 moles of this react to produce 1 mole of that. That's what I mean by stoichiometry. The total ionic equation has, well, how would I put the total ionic equation? It shows all species as they are in solution. As they are in solution. And I'll put air quotes around it, and I'll put real quotes around it in a minute. But remember last lecture, we drew hydration shells around all things that are aqueous? When you write aqueous in parentheses, you're thinking there's a hydration shell there. It also includes coefficients. So as I wrote the total ionic equation, I'll write 2K plus and 2I minus. And so our picture of what that means is that we do not have potassium iodide with the potassium and the iodide right next to each other. We have potassium and iodide floating around in solution. And that's what these pictures are attempting to show over here. They're not together. They're surrounded by their hydration shells. And writing potassium iodide like this does not really represent what it's like. This is a better representation. Okay, well, that's the potassium iodide, good. And rules for going from overall reaction to TIE. The rule is strong electrolytes break up into ions, period. Weak electrolytes, we will see, do not break up. Non-electrolytes, of course they don't break up. Solids, liquids, and gases don't break up. So, as you go from overall to TIE, strong electrolytes break into ions. And that's sort of akin to when my daughter does punch buggy and she says no punch backs, it's like, well, that ends it. So strong electrolytes break into ions, period. If you have a solid, a liquid, a gas, a weak electrolyte, or a non-electrolyte, they all stay together, they don't break up. So keep that in the back of your mind as we go. Nothing else breaks up. And you can see that it's important to know what is a strong electrolyte. That's where we're going. Any questions so far? All right. Then we do our lead 2 nitrate. This is aqueous. We have 1 lead 2 plus ion and 2 nitrates. And I'm going to end up with all of my TIE reactants on one line, and then I'm going to continue underneath with an indent. Then I get 2 potassiums on the product side. I do work on my board work, and I apologize for this. There, maybe that helps. These are the products now. Now, lead 2 iodide is an ionic compound, but it is not a strong electrolyte. Remember, the definition of any type of electrolyte is it dissolves, and lead 2 iodide doesn't dissolve. So this is the total ionic equation. Now, if you've done total ionics and net ionics before, so can anybody tell me what you cross out in the total ionic to get the net ionic? What are they called? Anybody know? Do you cross things out?
Yeah.
Yes. Do you cross things out that are on both sides?
Yeah.
But maybe, do we know the name, Johnny?
Spectator ions?
Spectator ions, yes. Spectator ions, thank you. Those are called spectators because they are not part of the reaction, meaning they are present on the reactant side. They are present on the product side, which means nothing happened to them. So, with my third color, nothing on my sleeve, really cross out the things that are on both sides. But it is actually important to know that term spectator ion, because some of the multiple choice questions you might see say, what are the spectator ions? Spectator ions are the ions that don't participate in the reaction, and you can think of them as such. There's one other spectator ion. Which ion is it? Nitrate is a spectator ion as well. And what you will see is that not only does the type of ion have to match, and match exactly, but so does the coefficient. Good. And then for the net ionic equation, I'm going to cross out spectator ions and write what's left. And yes, I like the phrase, write what's left. Okay, so we write what's left. We have 2 I minuses and lead 2. It doesn't matter which order. I tend to write them in the order they occur in during the TIE. I get 2 iodide ions plus 1 lead 2 ion make lead 2 iodide solid. And this is a perfect place to talk about the definition of a chemical reaction. In a chemical reaction, bonds are made, bonds are broken, or both. That is the definition of a chemical reaction. There are only 2 types of bonds in chemistry: ionic and covalent. Do not mention hydrogen bonds. Those are intermolecular forces, as we just said. So there's only 2 types of bonds, ionic bonds and covalent bonds. Which type of bond was formed here? Has to be an ionic bond, thank you, because we have ions that are coming together. So, and what I love about the net ionic equation, and really, if the question is, why do we put you through this hell that is overall total ionic and net ionic equation? It's so that you can focus on the species that are actually reacting. So, and I have asked this before, when you get to the net ionic equation, I have asked, what type of bond is formed? And you would say, an ionic bond is formed right here. is sort of the same, so for the period. Now, and to be a true chemical reaction, bonds must form or be broken or both. And if you keep that in the back of your head, you can always ask, is this a chemical reaction? And we'll answer that question several times throughout the semester. Combustion, definitely a chemical reaction. Dissolving. Dissolving takes a solid. Well, that'd be interesting to think about dissolving. If you take an ionic compound and it breaks into ions, then you're breaking an ionic bond. I don't know. We'll have to think about that. This is definitely a reaction because bonds were made. Any questions about this? All right. Yes. Let me check my notes. At some point, some of these become companion problems. This one is going to be a companion problem. CP is my abbreviation for companion problem. And what you will see is that on homework 4, I ask you to do 4 of these. And you, since you did a lot of them, those of you who took Chem 300 may be comfortable with them. Anyway, the goal is to be comfortable with these no matter how many it takes for you to have to. All right, so we're going to skip that one. I know we're going to do at least one more. We're not going to do all of this, but we'll talk about it, see what happens. Potassium iodide and silver chloride. Well, let's at least write the reactants here. And no matter what the reactants are, I can ask you to write the products. For double replacement reactions, you always take the positive of one, pair it with the negative ion of the other. We get potassium chloride. That's okay. Potassium chloride is aqueous. We get sodium iodide. And everything in group 1, so everything with sodium, everything with potassium will be soluble. Most things with halides are soluble. Everything's aqueous. Was there a chemical reaction here? No. And if you go through the process, what you will see is that these are all strong electrolytes. They will all be ions. They will all be spectators. They will all cancel out. And if you do the process right, you will see that there is no reaction. And but sometimes you have to do that, and that's fine. I'm going to sort of summary. All species are strong electrolytes. All ions are spectator ions, comma, no reaction. And that's an option. So sometimes everything's a spectator ion, and your point is there is no reaction going on. Questions about this? Oh, I already did that. Oh, this is the picture. You pour two things together, nothing happens, no reaction. Now let's talk about acid-base reactions. Acid-base reactions are a second type of double replacement reaction. Neutralization of the acid and base produce products that are water and a salt. Section 4.7 for those of you following along in your textbook. A couple things we want to say. One, how many strong acids are there? 7. Have you memorized them yet? Will you memorize them?
Yes.
Can anybody tell me one of them?
HCl.
HCl, another?
H2SO4.
So I heard you once, Leo. Somebody else. Who said there's another one?
HBr.
HBr? Somebody else? HI? Somebody else? H3PO4. Turns out it's a weak acid. Yeah. Not somebody else? Okay, this is where it sort of stops. It's H2SO4 sulfuric is one. Nitric acid. And those are really the 5 most common. Those are the ones you probably saw in Chem, and you will see in Lab 3 in Chem 400, and you'll see, you probably saw in Chem 300 in Utopia. The other 2 are less frequent, chloric acid and perchloric. Okay. Now, so please do memorize them. They will show up, as they just did. Strong acids are also strong electrolytes. Which means that strong acids break up 100% into ions. Weak acids, it seems like we mention them almost every lecture. That's how important they are. We said weak acids were really of 2 general forms. They have a COOH group. You know, I almost always list it as COOH when I make up quizzes, exams, and homeworks. Some textbooks list it as CO2H. Anyway, they're the same thing. Or H is in the front. And if their H is in the front, you have to memorize your 7 strong acids to tell them apart. Otherwise, just look for the COH. Weak acids are also weak electrolytes. And we'll talk more about them, but for now, next is strong bases. For strong bases, there are 1 group, literally, of strong bases that you have to know. Those are the group 1 hydroxides. Sodium hydroxide, lithium hydroxide, potassium, rubidium, cesium hydroxide, etc., etc. Actually, no, not etc. That's all of them. Now, here's what I'll say about Chem 400. The list of strong bases that you have to know for my class is that. There are more strong bases, but if you see a strong base on an exam or a homework, it will be one of these. We will wait until Chem 401 to expand that definition of strong bases. Okay? Fair enough? Strong bases, also strong electrolytes. weak bases, ammonia, NH3, and amines. The only one that ever shows up on exams is NH3. And really the focus of our class, we're going to spend much more time on the acids and a little bit of time on the bases. And we'll explore the rest of the bases in second semester. Weak bases, also weak electrolytes. Now we'll do a overall TIE and NIE for a acid and a base. Here it will be important to know what kind of acid and base they are. Hydrochloric acid, as you can see, is a strong acid. Sodium hydroxide, NaOH, strong base. When we write them, we'll write them as HCl aqueous. Plus sodium hydroxide aqueous. Like it says, and again, I can ask you to write this kind of reaction. I can give you these two reactants and ask you to write the products. It's double replacement, meaning that I have H plus here. I have hydroxide there. The first product's going to be water. The second product's going to be sodium chloride. And according to our solubility rules, and everything our entire lives have been about, sodium chloride is aqueous and does dissolve in water. Now, strong acid, strong base, those are strong electrolytes. We said as we move from our overall to our TIE, strong electrolytes break into ions. And then we said, or I said, period, because nothing else breaks into ions. We'll break these into H plus and Cl minus, both of them aqueous. We'll do the same thing for sodium hydroxide. All right, so it's at this point that I always write, midway through my total ionic equation, I go to myself, crap, I forgot to check to see if it's balanced. This one is. Whew. Anyway, I always forget that step until I get here and I'm like, well, how many ions do I have? Anyway. This time it all works out. Not a strong electrolyte. That's a liquid, stays together, comes down into our TIE as H2O liquid. The sodium plus and the chloride minus, those do become aqueous. That is a strong electrolyte. TIE to NIE, cross out spectators. My cute name for spectator ions, taters. No, let me cross them out. Cross out the sodium and chloride ions. My net ionic equation shown there. What kind of bond is formed, ionic or covalent?
Covalent.
This time it's covalent. A covalent bond is formed. This is a chemical reaction. Good, we're in the right place. This is chemistry. Next question. Since all strong acids are strong electrolytes, and all strong bases are strong electrolytes, I know, so I lost myself there. This isn't a question. This is just an answer. This is the net ionic equation for no matter what strong acid or strong base you put together. It will always look like this. Because they'll always break up. They'll always have some sort of spectator ions. This is true. So this is the NIE for all strong acid, strong base reactions. We probably won't do it very much in Chem 400, but when you get to Chem 401, Chem 401 is, there's like 3 chapters just on acids and bases that goes into a lot of depth. And so you're going to write these abbreviations for strong acid, strong base so much, we might as well just start using them now occasionally. So SA for strong acid, SB for strong base. Question, Matt?
Yeah, what is the word after strong bases?
RXNS for reactions. Thank you. It's my abbreviation for reactions. Thank you. Any other questions? Yeah, Hector?
Wait, so like hypothetically, if you mix those two, like after the acid and the base together, like you be able to drink it? Like you take pictures in the water?
Could you drink hydrochloric acid mixed together with sodium hydroxide? Not on my watch. However, if you were, and we'll talk about this coming up, but if you add stoichiometric amounts, and both of them are limiting reactants, so there's none left, you would only have water and sodium chloride. In theory, you could drink it. In practice, you can't be that specific, so you would never do it. But yes, in theory, right? Hypothetically, anyway, good question. Any more questions? Yeah, Alicia.
In regard to weak acid structure, like, do I deduce something as weak acid because it's not on a list, or because it has that, RCOOH?
For weak acids, right? Okay, so there are thousands of weak acids. So the way that you tell a weak acid, here's a question. Lactic acid. Is that a strong or a weak acid?
I just thought anything that's not on the list, of the short list of strong, is
Absolutely. So lactic acid, I didn't even show you the structure. But you know it's not one of those 7. It must be a weak acid. Right?
You have
Yeah, go ahead.
Sorry, you have the R-COOH on the guide you posted?
Yes. R just means rest of the molecule. So I know I didn't put it here, but sometimes I did put it on I think it's on the nomenclature sheet, isn't it? Yeah. It just means rest of the molecule. So, and here I didn't draw it, but this means the C is bonded to something else. Any other questions? Good question. Good. Okay. All right. Now, if I'm not mistaken, now let's deal with acetic acid. Acetic acid, not one of our 7 strong ones, must be weak. We'll at least start this one. We may finish it. Now, before I do this problem actually, let's take a minute for ourselves. So if this was your exam, and I like to talk about the exam because now it's 2 weeks away. And what I've told you about the exam is I want you to be as familiar with the exam as possible so you feel as comfortable as possible during the exam. Okay? So if this question were asked on the exam, it would be a little different. I would actually give you the formulas. But then I could ask you to do this problem. Because on your exam, everything, with one exception, is what I would consider a one-concept problem. Okay? That means that since this deals with overall TIEs and NIEs, which is one concept, and nomenclature, since I didn't give you the formulas, that's two concepts. That's too many for the bulk of the questions on your exam. So your exam will be easier than this problem. When you see this problem on the homework, it will look just like this with the names, but on the exam, it would have formulas. Okay? So your exam is going to be one concept problems with one exception. That is the last problem on the exam. The last problem on the exam will be 10 to 15 points. It will be multi-concept. It will be the hardest problem on the exam. And you will show me that you can not put together all of these concepts on the last problem. So the last problem on the exam, and you can see my old exams to see what last problems look like. So you will at least know that. They are hard. Okay? And in my mind, if I can put one pretty hard problem on the exam, it allows me to make the rest of the exam a little bit easier. Okay? So you should not expect, I mean, yeah, all of Chem 400 is a little hard, but you'll see problems that are very similar to the homework for the rest of them. But there is one, I call it the last question on the exam, and it's meant to separate, honestly, the A's from the B's. Now everything else, you're playing along at home, should be straightforward. On the last problem on the exam, you should never leave it blank. In fact, you should never leave any question on my exam blank, because if you have grams of something and you turn that grams into moles, it's probably worth 2 points. And you may not know why you're doing it, and I'm okay with that. What happens for me when I solve problems that I don't know what the answer is, and I just start doing something that I do know, it jogs my memory, and I can then answer the rest of the question. Sometimes I'm just still completely lost. Sometimes you'll write a whole page of crap, and it won't be worth anything. But I will tell you one thing, if you leave it blank, you will lose all the points. Okay? So, do your best. And I realize there's time considerations, and I will do my best. Here's the other thing about my exams. I'm giving you that extra 10 minutes. Because as much as possible, I try to make my exams not races. I want you to have enough time to put everything you can down on the page. And it's not perfect. An hour. There are some people, you give them an hour-and-a-half exam, and they're going to want to take 3 hours no matter what. But anyway, we'll see. What I suggest is you prep for the exam. You have 3 practice exams. Certainly the week before, you want to take 2 of those and have them be open book. That's fine. But the third one, take it in an hour-and-a-half. See how you do. Okay? That's how long we typically have, even for those exams, is an hour-and-a-half. Anyway, so that's a little bit more about exams and what the questions will look like. It is true, and I apologize, there is one thing up my sleeve. It's the last question on each of your midterms. It's tricky, and it's meant to be challenging for everyone. Okay, so back to this problem. We now have our formulas. We know that this is a weak acid because it's got the COH group. We know it's a weak acid just from its name because it's not the name of one of our 7 strong acids. For the overall reaction, nothing happens. You just write formulas anyway. This particular one, we have K plus and hydroxide. Here, this is an acid. It still has H plus. So H plus is our cation here. Hydroxide, we still make water. The other species, the other ionic compound is potassium acetate. And so you still put them together like that. All right, now previously in the last problem we said strong electrolytes break into ions. Is this first thing a strong electrolyte? Or is it a weak electrolyte?
Weak.
It is a weak electrolyte. Do not break it up. The whole thing comes straight. Right? The rule is only break up strong electrolytes. This is a weak electrolyte. Keep it together. The explanation, or some of the explanation, is that 95+% of acetic acid in solution is whole molecules. Whole molecules are the dominant species. Whole molecule is dominant species. And for the total ionic equation, what we're trying to do is we're trying to represent what is in solution. That's why we break up all the strong electrolytes, because it's not really potassium hydroxide stuck together. It's potassium ions and hydroxide ions with their hydration shells. See down here? That's another hydroxide ion floating away. So in fact, acetic acid has its own hydration shell around it as whole molecules, sort of like sugar would or other ones. Still dissolves, still has a hydration shell. I have not drawn you a hydration shell for either a whole molecule because it gets kind of complicated, and we need intermolecular forces to really talk about it, and that's not until chapter 11. But it does have a hydration shell. That's what aqueous means. It's much easier to think about the hydration shell around a K+. Alicia?
The reason you write it as CH3, I memorize it as C2H, that's an ion.
Like this?
No, I confuse it with an ion, C2H7O2 minus.
There's lots of ions with carbons, hydrogens, and oxygens in them.
It's almost as if H is redundant to there.
Yeah. I would say, let's talk about it outside of class.
Yeah.
But it's a good question. Now, this is, how many people in their Chem 300 saw acetic acid like this? Anybody? Some of you? This is what your textbook has, by the way. How many people saw acetic acid like this? Okay. This is the version that is more like you will see it in organic chemistry, because it shows you a little bit more about what the structure of the molecule is. It does have a CH3 group in it. Anyway, so that's why I use this, but there are different ways of organizing the C's, H's, and O's that are useful in different times. Okay. That's very poor form because that looks like an arrow telling me this is a product. It's not a product, it's another way for that. Liquid stays together. Write the same formula in the TIE. And that says CH3COO minus aqueous. That is the acetate ion that we've broken down with its negative charge. Well, let's see what we got. As we go to our NIE, we cross out spectator ions. There's only one spectator ion this time. What is it? Only K+. It is the only thing that is literally exactly the same on both sides. This is important. CH3COOH is different than acetate with a minus sign. That's what we mean by differences. If they're different in any way, keep them in and write it. And we get acetic acid plus hydroxide goes to water plus acetate ion. Were bonds made? We took a hydroxide, we added the H plus to it, we made a covalent bond here. Were bonds broken?
Yes.
This H was removed to make acetate. In this particular case, covalent bonds were made, covalent bonds were broken. And that's possible, right? So, covalent bonds. Covalent bonds were made and broken. Probably broken first, but Brenna and Maddie. Brenna?
That's a single displacement reaction, right? On a double one?
Is this a single or a double replacement reaction? This is still double. And we entirely, if you're trying to separate the two, we only, well, we'll do a couple of examples, but we spend a lot of time on double replacement, and then we'll spend a little bit of time on single replacement. You can tell a single replacement reaction, incidentally, because it has something by itself, not an ionic compound, plus an ionic compound, or in this case, yeah, strong acid. So, anyway, does that answer your question, Maddie?
That was mine.
That was your question? Yeah. Good. Any other questions? Leo?
Yeah, I can't tell where the covalent bond was broken. Is that in the acetic?
Oh, yeah. Right. So see how we have an OH here?
Okay.
And then the H is gone. That's the bond that's broken, was this, that one.
And that's covalent.
And that is covalent, right? Those are the dashes. And I know we haven't gotten to that yet. We haven't drawn Lewis structures, but yeah, that's, yeah, does that answer your question?
Yeah.
Yeah. Other questions? All right. It's not 2:30 yet, so I can keep going. Companion problem, formic acid and sodium hydroxide. Formic acid is a weak acid. I'll have you look up the formula. Gas evolution reactions. Another type of double replacement reaction. This time one of the products is a gas as a result of a breakdown of one of the products. There are two possible products, and let's say this. If your reaction makes carbonic acid spontaneously breaks down into water and carbon dioxide gas. And we're about to see it happen right here, but if H2CO3 is a product, replace it with H2O and CO2. If carbonic acid is a product, replace it with H2O liquid and CO2 gas. So you will never have carbonic acid as a product. Well, you may for a minute. I've sort of used up all my space here, so I'm going to put the next one up here. There's an analogous situation where you form sulfurous acid, H2SO3. And that will spontaneously break down into H2O and sulfur dioxide. 99% of the time, if you're going to see this, you're going to see this one right here. You could see this on the homework or other places. This was a lot bigger back in the day when we were more worried about acid rain. Well, from a sulfurous acid standpoint, maybe its time is coming back as we encourage more coal-fired power plants, which will create more acid rain. However, I'm happy to not be talking about this personally. Because acid rain is a problem. Do we know what acid rain is?
Yeah.
Have we heard about it? Is it a huge issue like it used to be? Does anybody? No. We cleaned up our air. That's a lot. Anyway, bad news. Air's getting worse. All right, so sodium bicarbonate. So as an example of this, sodium bicarbonate and hydrochloric acid. Sodium bicarbonate is NaHCO3-, also called sodium hydrogen carbonate. Plus hydrochloric acid. Both of those are aqueous. They are strong electrolytes. Sodium, well, let's just do this. H plus here from HCl and bicarbonate combine to form carbonic acid, H2CO3. And almost before the ink is dry on your page, you remember that carbonic acid gets replaced by H2O and CO2. In fact, you can do it the way I did it, where you put in the carbonic acid and cross it out, or you can just skip it and put in the H2O and the carbon dioxide. Either way is fine with me if this comes up, say, on your homework for an exam. Strong electrolyte breaks up. Strong electrolyte breaks up. Liquid and gas do not break up. Strong electrolyte breaks up. When you get to the bottom here, what you're left with is bicarbonate ion plus H plus makes water and carbon dioxide. So I'm going to skip down to that. Now, covalent bonds are formed. It may not be that clear which ones are formed. Maybe some of them are broken as well. How this happens is a little bit complicated, but definitely there's enough rearrangement here that bonds must be formed and broken. This is a chemical reaction. Any questions about this? All right. How are we doing? 130. What happened to sodium chloride? So I skipped the TIE, and they were spectators. I just went to the NIE. Oop, blew right by that one. Oh. See the bubbles? I will say this, when you do lab 3, the bubbles occur very quickly. So you have to pay attention, otherwise you miss them. That's the end. We'll now start lecture 4. Let me pull that up. Those are the companion problems. Let me actually pull up. Okay, so here's what I want to say about lecture number 4 and the first problem that we're going to do. It's a great problem. we're going to save it. What has happened is we're getting, I want you to let's say this, we're going to come back to this closer to exam 1 because this is actually a pretty good example of a pretty hard problem. So skip it, and we'll come back to it. We will, by the way. There's actually 2 problems. The first one we do in lecture and another lecture or 2. The second one's a companion problem. Its answer is already published on the Chem for Under website. Where we're going to pick up lecture 4 right now is our 4th reaction type, redox reactions. And we've already covered our first 3 types. Here's what I can say about redox reactions. I will not ask you to write redox reactions. On exams, on homeworks, well, the exams are what we mainly care about, so I'll just say exams for there. You might have to write some redox, or you will have to in a lab, but I'll be there to offer support. Now let's talk about, but I can and will ask you to write combustion, dissolving, and double replacement reactions on the exam 1 and subsequent exams. Now let's talk about the oxidation number. My abbreviation for oxidation number is capital O, capital N, also called the oxidation state. If I were to define the oxidation number, I would define it thusly. A hypothetical charge assigned to each atom a hypothetical charge assigned to each atom that allows us to keep track of electron movements in reactions. Now, I have an abbreviation for electron. It is E superscript minus, and I will use it a lot. Some people would say that all of chemistry is keeping track of where the electrons go. That allows us to keep track of electron movement. Redox reactions involve the transfer of electrons from one species to another. That's what I'm talking about as the electron movement. From one species to another. Now within that, there will be redox reactions is actually an acronym or an abbreviation in and of itself. There will be an oxidation half reaction. In the oxidation half reaction, one element will lose electrons. And in the oxidation half reaction, electrons are considered a product. Electrons are considered a product. There's also a reduction half reaction. One element will gain electrons, and electrons are considered a reactant. Now, I'd like to add something else. For oxidation half reaction, the element will lose electrons. Electrons are negative things, so the oxidation number of the element will become more positive. And that's how we'll tell when something has been oxidized. For the reduction half reaction, one element will gain electrons. Electrons being negative things, the oxidation number of the element becomes more negative. So you gain something and you become more negative. Now, how many people have done oxidation numbers before? Some of you. There are lots of ways to assign oxidation numbers and keep it organized. I'm going to show you my method. You can use it, you can not, as long as we all end up with the same answers. And I have a set of guidelines. First guideline, number 1, the oxidation number of each free element or free uncombined element is 0. I'm going to use ON as my abbreviation for oxidation number. The oxidation number of each free uncombined element is 0. Now, for me, I have 3 examples right here. My board does not have lines. Your notes do not have lines. So I'm going to draw some lines in there. And on the line underneath each of these, I will write ON. And then this row will be the oxidation numbers. And it's always the oxidation numbers that I'm looking for. And the oxidation number of sodium is 0 because it's by itself, no other elements. The oxidation number of chlorine in Cl2. And so this is, they're all zeros because they're all by themselves. I wanted to show you what free uncombined elements look like. You probably already knew, now you know for sure. Any questions about that? If not, then guideline number 2. The oxidation number of each monatomic ion, mono, one atomic atom, each one atom ion is its charge. The ON for each monatomic ion. The oxidation number for each monatomic ion is its charge. Sodium plus, its charge is +1, its oxidation number is +1. And I'm not picky about it. If you just wrote plus there, or if you just wrote 1, those are fine indications of +1 for me. I typically, because I want to stay organized, put the number and whether it's positive or negative. Chloride -1. In the ionic compound sodium chloride, do we have sodium ions and chloride ions? We do, actually. Yes, that's the tricky thing. So sodium has an oxidation number still +1. That's what I'm trying to get at. Chloride -1, and they add up to 0. And for so many reasons. Yeah. But what I want you to know is those are monatomic ions in that formula. Questions about that? All right. Well, we haven't even seen any oxidation or reduction yet because we don't even know what the oxidation numbers are to see if they change. We have two more guidelines. These are, again, my made-up set of guidelines. Your mileage may vary. Guideline number 3, the sum of the oxidation numbers of all atoms equals the overall charge on the species. The sum of the oxidation numbers on all atoms equals the charge on the species. And by species, I just mean it could be an atom, it could be a molecule, it could be an ion, as we'll see. Guideline number 4, in compounds, the oxidation number for hydrogen is +1, except in hydrides when it is -1, which would be confusing, except we never see hydrides. So hydrogen is +1. In compounds, the oxidation number for oxygen is -2, except in peroxides when it is -1. And I think I've mentioned this before, but I'm going to mention it again. So things in parentheses, you don't need to remember. So you do not need to remember them. If you need them, I will tell them to you, even on an exam. Okay, so now we're going to do actual compounds. And what I like to do for compounds is I like to break each of the elements up. It's kind of messy, but we'll try it. Because hydrogen has an oxidation number, oxygen has an oxidation number, you will always report the oxidation number for every single element. By rule number 4, what's the oxidation number for hydrogen in a compound? +1, right? Oxygen in a compound?
2.
-2. Now, there are 2 hydrogens, and so if I'm keeping track of all of the atoms, I might have a +2. And this is where I put my work. And my work would say there are 2 +1s, that's +2. There's 1 -2. And the whole thing has to equal 0 because there's no charge on this molecule. Okay? Now, I don't care if you do this work down here. I will only be grading your oxidation numbers. Sulfate.
So that's per individual atom.
It is always per individual atom. That's a very good point. Now, I don't have a rule about sulfur. I have a rule about oxygen. What is the oxidation number of oxygen? -2. The only time oxygen is not -2 that you have to remember is when it's O2 by itself, then it's 0. And what will happen is, at most, there's one thing that we don't have a guideline about specifically, and you'll have to use rule number 3 to find out what it is. And that's what we're going to do right now. We have 4 oxygens. 4 times -2 is -8. The overall charge on sulfate is -2. Mathematically, you can either plug in an x here or what have you, but x -8 equals -2 plus 6. And the plus 6 goes right there, and there's only 1 sulfur. So that means its oxidation number is +6. Now, do you remember On the previous slide that was right there, I said, these are hypothetical charges. There is no such thing as a +6 charge on anything. Sulfur cannot lose 6 electrons ever. That's what I mean by hypothetical. And this hypothetical charge will still help us keep track of electron movement. So it's still useful, even if it's not true. Any questions about how I got this +6 on sulfur? Oddly enough, in chemistry, in Chem 400 and Chem 401, the biggest positive charge you will ever realistically see is +3. The biggest negative charge is -3. And that's a lot of charge. So this is an oxidation number. It's hypothetical. Let's see. We'll leave these two for you to do at home. We'll skip down here because we only have 3 minutes left. And let's see. We'll do a couple of these. Let's do those 3, and we'll leave the rest of them for later. We do not have a rule for nitrogen. We do have a rule for hydrogen. It's always +1. There are 3 of them. So our hydrogens are +3 as part of our work, our process. We know that there's no charge. We know that nitrogen total has to be -3. There's only one nitrogen. Its oxidation number is -3. Actually, let's skip all these and come over here. Nitrogen dioxide, we have a rule for oxygen. There are 2 of them that adds up to -4. What is the oxidation number on the nitrogen in NO2? It's not +2. It's +4, yes. And we're starting to see the variety of oxidation numbers that a nitrogen can have. Not that we'll ever have a nitrogen that's truly +4, that is hypothetical. And we'll talk about why that is. Let's see. Well, we have 30 seconds left, so why not stop now? Yeah, so we'll pick up there. Next week in discussion, we are doing pH.